now that we've settled on the title, yeah, I'm going to talk about something of this nature, or close to this, okay? So, well, I should start with thank you to the organizers for inviting me here to speak. It's a pleasure to finally be back in Miami. I spent a lot of time here in a past life, like, I guess the days before COVID feel like a past life now. So I'm happy to be back, and always, I'm coming from University of Minnesota, so you can imagine that the weather's a little nicer here. All right, so let me start with the theorem of somebody you may have heard of, David Hilbert, not David Favero. Hilbert, so let M be a k adjoint x1 through xn module. Then M admits a free resolution of length at most n. This is, of course, Hilbert's syzygy theorem, and we know that this is basically the condition for being, or equivalent to being, a regular rank. And then let me also say a geometric version. So Grothendieck. Okay. So Grothendieck says that let X be a smooth variety, okay, of dimension n. Then any coherent sheaf or if you like quasi-coherent, but I want to say the word vector bundle. So any coherent sheaf F admits a resolution by vector bundle. Okay, and we know this is affine space. Vector bundles on affine space are trivial, i.e. free modules. All right, and then so you may say, okay, this is it, right? Can we ask for anything more? We could ask line bundles, which in general is not true, right? But we can conjecture that in nice scenarios it is. So conjecture of Burkesh, Ehrman, Smith, let X be a smooth, so I'll state it the way that they conjectured it, smooth projective toric variety. And I'll put projective really in parentheses because it won't actually matter. Yeah? Then X of dimension n, then X, then any coherent sheaf F on X admits a resolution by line bundles. Of length. So that's second time. So this is a reasonable thing, right? Of course, I can just take, essentially I could try and do Hilbert's syzygy theorem, right? And I'll get that any coherent sheaf. So I can go to the Cox construction and do Hilbert's syzygy theorem, just like I could do this for a sheaf on projective space, but if I did this for projective space, I'll get one more than that, right? Of course, there's a way around that, but on a toric variety, I'll get something like the dimension plus the carbon if I resolve it just as a module over the coordinate ring. Okay, so a little more work has to be done. We know that there's a resolution by line bundles, is what I'm saying, but we don't know it's of length n. We know that there's a resolution by vector bundles of length n. All right. So I want to say one more kind of formulation in the same spirit of this conjecture. So for this, I want to think about the derived. So if x, the derived category of x equals bounded complexes. So the objects are just bounded complexes. So now instead of talking about modules, I'm working and resolutions, I'm working just sort of in the category of those objects. Okay, and so this is objects, and morphisms are like R-hom of complexes. And I don't want to say too much about this. So this is just some category whose objects are complexes, okay? And so really it's the localization by maps inducing isomorphisms on homology of the category. Okay. So what I want to say is that in this category, resolving a complex, a module corresponds in the derived category of X. So I don't know, modules. This corresponds to taking mapping cones. So taking a sequence of mapping cones. So this is a natural operation we have. If you like, this category has a triangulated structure. This is taking a sequence of triangles in that structure. So related to this conjecture then of Burkish, Ehrman, Smith, we can say a conjecture of Orlov. So let X be a smooth variety, okay, of dimension n. Then there exists a G in the derived category of X, so a complex, or maybe just like a finite collection of sheaves, okay? You think of, or one sheaf, but with finitely many summands, right? One coherent sheaf, okay? Such that all complexes or in particular all sheaves, right, can be obtained by at most n mapping cones or triangles. from G. Okay, so if you've seen this before for experts, this means that the Rouquier dimension, this is my way of saying the Rouquier, this is a notion of Rouquier dimension of this category, and this is saying that the Rouquier dimension is equal to Krull dimension. That's the title of the talk. Okay. But I think I avoided any mention of Rouquier dimension in my notes. Questions?
So the conjecture is smooth algebraic variety, no conditions, like quasi-projective or anything like that?
I don't think I don't think he has any conditions. You know, you can have, of course, if you have quasi-projective, then you have like nice natural generators, like sums of ample line bundles. But in general, you can have an ample family of line bundles, and those will generate. These are certainly still finitely generated, so there's no reason to assume projectivity. At least because there's no counterexample. Okay. Yeah, any questions? Okay. So I want to state, so I'll leave both conjectures up there. So the good news is this is no longer a conjecture. Bad news is this still is. So they're on. So this is joint. I should have said at the beginning. This talk's based on joint work with Jesse Huang, and this was also discovered independently by Hanon, Hicks, Mazarev. So one, BES is true. And two, Orlov is true for normal toric varieties. So, I mean, maybe normal is implicit in some people's definition of toric variety, in which case all toric varieties, right? The toric varieties which come from fans. Okay. So, and I want to now say the proof, which of course is quotations, because I'll say about 2 sentences about the proof. Okay. This proof is actually a direct construction. But these 3 people are all symplectic geometers. So you can guess that it's inspired by homological mirror symmetry. And our proof, I don't know why they don't get dashes, but we do. So our proof actually just uses homological mirror symmetry. So you have the derived category of a toric variety. Homological mirror symmetry tells us this is some kind of Rouquier category. So I'll put a bunch of symbols here and maybe explain more in a second. So it's the Rouquier category of the cotangent bundle of the mirror torus. Which stops, the wrapped Rouquier category, which stops in some data associated to the fan. So I'll say more about this in a moment. But the point is that then we can try and count we can try and solve these conjectures here. Okay? So here, this actually turns out to be generated by natural set of Lagrangians G, okay? And that G generates all other Lagrangians in time N, right? So that's Orlov's conjecture, okay? So, while there's no natural thing to pick here, once you have this geometric model for the mirror, so that's not canonical, right? But there is such a geometric model for the mirror, then it comes equipped with a natural set of generators, okay? So, and then when you translate it over, that natural set of generators, if you're smooth, corresponds to line bundles. In general, I'll still use this notation, O of D, where D is in the class group of X sigma. And now if this toric variety is not smooth, this is some sheaf, okay, associated to this divisor. Okay. So if this is not Cartier, some of them may be Cartier, but not all of them. So these can be some line bundles and some just sheaves.
Isn't there some proof of this fact by some French guy, Chinese guy whose capacity to
They have papers on, that's right. So maybe I can say more about that. I don't think, so they say something about when you have a triangulation, right? And that's essentially what we'll use.
So this complexes versus that you'll be using relate to their skeleton.
Maybe I'll talk about it with you afterwards. I'm not sure. Okay. So I'm going to get to skeleton though in a moment. Okay. Yeah. So the idea is that actually, in general, on any normal toric variety, even if you're not smooth, you can still build a resolution by these sheaves of length n, of any sheaf. Okay. Which sort of isn't obvious from the algebra. You know, if the resolutions are much longer, like if you even take the minimal resolution, it will in general be longer. So these resolutions are really, algebraically, they're complexes of free modules, right? Well, okay, in the smooth setting, well, actually, no, even not in the smooth setting. They're always complexes of free modules in the coordinate ring, okay? But their homology lies in the irrelevant locus for the short variety.
So you're saying
So
you
they're not really resolutions, right? They have homology, but in the irrelevant locus. So
you're saying you build a resolution made of these sheaves, which, when in the smooth case, they turn out to be line bundles. In general, they're not.
That's right.
So the result says that you can build something
You can build a complex with terms
length.
in actually some finite collection of line bundles, of sheaves, right? So for any module, you can build a complex with terms in here such that its homology, H0 is the sheaf. So it's a resolution in that sense, right? Just not locally free, you know? Okay. All right, so yeah. So let's set this up. So some notation. So N and M, I already used M here, so what is M? Are dual lattices. And sigma is a fan in an R. Okay, so as we may know, a fan in an R can be interpreted as gluing data So just from the fan, right, which is just some combinatorial thing, the gluing data gives us the toric variety. So each cone, we take the dual cone, we take the stack of the group algebra on that on that monoid, and we glue them together along the fan structure. We get this thing, which is a toric variety, right? And on the other hand, we can form a Lagrangian here in this cotangent bundle. Yeah. So we take sigma cross sigma perp, the union over all sigma and sigma of this. And this thing lives in, well, sigma is a cone in NR, right? Sigma perp would be an MR. And I view it, I view its image really is what I mean here inside this torus. Okay? And this thing, of course, is just the cotangent bundle of what I'm calling the mirror torus. Okay? All right, so this is a nice Lagrangian in the mirror torus. All right. So, actually, homological mirror symmetry passes through microlocal sheaf theory. And it's enough to think of all of this in terms of microlocal as microlocal sheaf theory as the mirror in the setting. So what do I mean? This is an old story, I think, going back to Nadler and Zaslow. So the derived category of a toric variety is equivalent by originally in the equivariant setting due to Fan, Liu, Troyman, and Zaslow to the category of sheaves on this torus with singular support in this thing. This thing is, yeah, in this Lagrangian. And I'll explain what that means in just a moment, but I want to give the idea before
I think it goes back to Bondal, really.
Okay.
The first idea of this, and then.
Yes, fair enough.
Bondal and some Chinese.
Yeah, but Bondal came
yeah.
up with this.
Bundle and Ron.
And then written down. But
You're right. You're right.
If all did it on the equivalent, right?
That's right. And then I want to put another name here. You're right. So Kuwagaki did this, I think, 2018 or something like this. This is maybe 2009. Okay? Yeah. In general. Okay. So then there's also a theorem of Nadler-Zaslow and Ganatra Hardin-Shenda, which completes what we would call homological mirror symmetry to this Rouquier category I had written down. Okay. So for the purposes of this talk, we can look at this FLTZ or Kuwagaki equivalent. Okay. So this is what we use. And so let me define this thing. So definition, and again, people can correct me if I'm wrong, but I think this is Kashiwara-Shapiro. So if X is a real manifold, so e.g. Historis, right? Okay. And F is a complex, or just a sheaf, but maybe a complex of sheaves. I have to put a plural on X. Okay. Then the singular support of F is defined as the set of points X, zeta. So X is a point in X, zeta is a cotangent vector, such that, so let me just put, this is in the cotangent bundle to X, right? Such that, if I take the stock of the local cohomology on the positive part of some function, of this sheaf, or this complex of sheaves, at X, I take its stock, it's not 0. For some function defined in the neighborhood, a small epsilon neighborhood of X. This is continuous. Actually, differential.
Y is theta, right?
Oh, yeah, such that, sorry, thanks. F of X is 0, and df of X is zeta. So anyway, this is some subset of the cotangent bundle, right? So, the support of the sheaf lies on X. The singular support is a more refined notion of the support of a sheaf that lies in the cotangent bundle, and makes sense on a manifold. Okay. So now we can define this category. I'll erase this. Maybe I should have left it. So let gamma be in here closed. Oh, and actually, there's one more thing, that you take the closure of this set. In general, I don't think it matters for the purposes of what we're talking about. Okay. So let gamma be a closed subset of this. We can define this category, sheaf X sigma. So this notation actually means sheaves. In this setting, people mean complexes of sheaves. So this is actually a full subcategory. And now we need some notation, d sheaf of X. When we say dx, we mean the derived category of coherent sheaves on X. Here I mean the abelian sheaves on X, just usual sheaves on a real manifold X. Okay? So this thing is a full subcategory with objects F in here, such that singular support of F is in this fixed thing. Okay? So now I erased it, but again, I'll write the theorem. so this was FLTZ Kawagaki, I won't write that again, was that this is sheaves on the mirror torus with singular support in this Lagrangian that came from the banding. Okay. Questions? So just a comment. This thing is generally not, like you could say, oh, I could take derived category of sheaves with singular support in this thing that's slightly different than what's being defined here. There are complexes with singular support in here, okay? But such that the individual terms of those complexes do not have singular support in here, because the singular support is defined using this derived, okay? So anyway, this is not the derived category of the Mendelian category. It's just some full subcategory of the derived category.
May I ask you what's the difference between the equivariant and non-equivariant statements? Why it took like 10 years? There was something, I don't know, between, must have been something not happening. Anyway, it doesn't matter. But I'm just curious.
Yeah, I mean,
if it's just formal stuff or must have been some.
I can tell you that the original proof by FLTZ, the point is that, you know, you like in all homological mirror symmetry proofs at the moment, you choose some generating set and you match them. And in the equivariant setting, those the maps are really simple. Right? They're one-dimensional in general. Like, if you have total equivariance, let's say on PN or something like that, you know, then hom from O to O of like 1, 1, 1, 1, 1, 1, 1, 1 is just, you know, that one monomial with exponents 1, 1, 1, 1, 1, you know, or you know, I could change the term, but you know, there's one monomial that's completely equivariant for the full torus. And so when they proved it, they used that. But Kawagaki's proof, you know, I don't think it's I don't think there was a big threshold for like. I just think it wasn't done. You know?
No, I think people tried. No, there were counter.
I mean, there were people that tried,
there were counter examples. I remember you can work them out. There were things. It wasn't definitely that.
Okay,
that's
so
for sure.
Well, I mean, maybe we needed the right. I mean, so there was work of Vivek and stuff like that, where like the right approach is basically via the Cox construction. So what Kawagaki does is really, he says that if you have a combinatorial equivalence via the Cox construction, then you get it. But essentially after that, it's just doing it locally. So you're basically saying, you know, on any toric variety via the Cox construction, I can do the check resolution of the irrelevant ideal. And you can match that to the micro. I'll talk to you more about that.
Sorry.
Yeah. Okay. All right. So, yeah. Okay, so I wanted to do an example. So this example certainly was worked out by Bundall for anybody else. Okay. This is P1. So example P1. Yeah. So the fan is a ray, and I'll label the cones. So the fan is, more precisely, is the set of these three cones. Okay. So then I get these pieces So in this case, sigma minus cross sigma minus perp is sigma minus cross 0. It's one-dimensional space, so if I have a full-dimensional column, the perp is 0. Yeah? And sigma plus cross sigma plus perp is also sigma plus cross 0. And then sigma naught cross sigma naught perp is 0 cross S1. S1 here is R mod B. Okay. So what's the picture? Well, this Lagrangian looks like the 0 section of this cotangent bundle. This is the 0 section of this cotangent bundle, so this is my 0 cross S1. And then I have this line, sigma plus cross 0, this other line, sigma minus cross 0. So I get the whole cotangent fiber over 0 in addition to the 0 section. Okay. It's the union of the cotangent fiber over 0 and the 0 section. Great. These aren't really intersecting. Okay. Yeah. So I'll say a little more here about how this works. Maybe it indicates how this proof will go a little bit. So I have 15 more minutes, right? Or maybe, yeah. So here I have derived category P1, and here I have sheaves on S1 on a circle with singular support in this thing I've drawn. Okay? And here I could take, for example, the structure sheaf of P1.
David, do you think about this like I have the mirror, which is the cylinder, and then I
Yeah.
have
Yes.
two generators.
Yeah, these are honestly the Lagrangians in this Nadler's Aslow.
Okay.
So, this is C0. So this is the skyscraper sheaf at 0 in S1. So S1 is R mod Z, so 0 in S1. That takes the value C. Yeah. And O P1 of 1 maybe goes to the extension by 0 of the interval from 0, 1, or this is by 0, 1, I mean the circle minus this 0. Okay. Extension by 0 of this sheaf, okay? And maybe O of 2 is a little more complicated. Sorry, OP1 of 2 is high shriek of 0, 2. I don't want to, if you haven't seen this, this is properly supported push forward. For pi is the map from R. That's one, covering space map, universal cover. And this is now this extension by 0 of this interval in R shrieks forward to the circle. Okay. Okay. So that's how it works. In fact, from the first two, if you know Valence's theorem, you could prove homological mirror symmetry by just calculating homs between these things and factoring it through Valence. Okay. So now, what is the natural? I told you there was a natural generator in this sheaf story, right? So what is that? So for any x, so for any point we get a functor. I mean, this is really on all sheaves, but I'll restrict this. I'll think of this as a functor from this singular supported sheaf category to the derived category of vector spaces, which is nothing but the stock functor. Right? So we can just take a complex of sheaves, and since okay, I think maybe when I said subcategory of all sheaves, maybe I should have said sheaves of C vector spaces. So and this becomes a complex of C vector spaces, taking stock, right? Okay. So Brown representability implies that this functor, maybe I should put co-representability, is co-representable. The stock functor is co-representable. i.e., there exists an object, Px, which I'm defining by the property com Px to any complex of sheaves is this functor, is the stock. And we're going to call this thing the stock probe. Okay? So the natural generator of this category is the sum over all stock probes. Because if a sheaf is non-zero, it means that it has some stock that's non-zero. So if I take the sum over all stock probes, those are going to see every sheaf. Right? Observe. Observe. Okay, sum over x and x is some infinite thing right now. Well, we'll see it's finite in our setting. Okay. Of stock probes, if I take Hom from this, it's infinite. Let me pull up this co-product. I need a product or a co-product, so let's just put F here. For now, it's going to end up being finite and not a problem. To some sheaf, this is product of the stocks, right? Which equals 0 if and only if f is 0, obviously. Right? Okay, but this implies this is a condition for generation. So this thing kind of obviously generates by the way that it's defined. And it's natural. It's just the sum of these stock probes is kind of a canonical thing you have in this setting.
Is it easy to say what this stock probe is?
Yes, but maybe I'll say only an example, and if you're interested, I can tell you a lot more about it. Yeah. I mean, yes and no. It's easy to say in some situations. Okay. So let's go back to this P1 example. Then there's two stock probes that are interesting. So when x is 0, the stock probe at x is this thing, which we said was the mirror to O of 1 on P1, right? And when x is non-zero, for any x non-zero, you get the same sheaf. So there's only two stock probes here, and it's this pi streak CO to 2, which we said was OP1 of 2. Okay. And I can tell you a lot more about why that's true, but I don't have time at the moment. So, okay. So now let's take the following general setup. So let X be a real manifold with a regular CW structure. So it's glued out of a bunch of cells. Okay. And that, I don't know, maybe I overuse zeta, but I've also used P, so I don't know. Okay, alpha CW. The cell coset. Okay. Then define the following thing. So you take the union over the singular support of the constant sheaf on the interior of each cell. So E in the set of cells, this is the open cell. Yeah, so the interior of the disk. Okay? And you take its singular support, it'll look like something. Right? Okay. So, and now let lambda be closed in this thing. Okay? Then, what's the good news? Well, this thing doesn't detect the difference between stock probes for if you're in the interior of the same cell. Okay, so then G is really a finite sum. So let me put finite CW. Well, okay, it's not a compact manifold. Yeah, so let's put finite CW. Okay. Then G. So an example we have in mind is a torus. Okay. All right. So then G equals sum over E in this self-hoset of GXE for some chosen base points. Is a generator, and it's better. It turns out here on this category, so it generates, but also what's hom between them? Well, by definition, they're stocks. Okay, and it turns out that yeah, when you write down what these things are, which I'm not going to tell you, you can just calculate their stocks. All right, and when I calculate hom, I get the incidence algebra on the CW on this CW coset. So it turns out that this sum G is a tilting object, and which yields an equivalence from sheaf on X with this CW skeleton to the derived category of the incidence algebra on the CW quotient. So what's good about that? This is a non-commutative algebra of global dimension n, where n is the dimension of the map. Okay, so what does that tell us? That tells us all of our theorems. Yeah. All right. So I know I have just a couple minutes here. So I'll just try and say that. So let me say, I just basically gave you the proof of this. The G generates if lambda is contained in lambda CW, G, which is the same thing, but with these stock probes now for this smaller skeleton, generates sheaf x lambda in time T of G, and T of G is between the dimension of X and as a finite CW complex, or as a real manifold, right? And the Lowy length of the cohomology. So e.g., X is a torus, then the time of G is exactly the dimension of X. So Lowy length, I mean the longest length of some product of cup product.
So what's the name of the precise? This is for toric varieties.
Probably -1, whatever. Convention on what the meaning of it.
But it's toric variety.
No, this is any smooth manifold X and any CW structure. Yeah? And for a toric variety, the point is it's subordinate to this CW structure given by Bundle and Ron.
So what about if you have feature blown up in 4 points?
That's a great question. So,
It's the next natural thing to do.
yeah, so don't you have moduli in that setting? You have 1 point.
Then when that's 8, no, actually in this case you don't. But, again,
So yeah, if you blow up too many, then right, then you have moduli.
5 is also.
And then usually these, so having this fully topological model has something to do with not having moduli. But 4 points, 4 points is probably possible.
Yeah, that's what I mean.
Yeah.
It's 4 times 2 for each point.
So
Modulo the 8-dimensional.
So I mean, we have I'll talk to you about this later, but we have a way to go to topology just from the exceptional collection. So you don't, we have some kind of straight to sheaf theory version from exceptional collections. And you can probably do that. Yeah. Okay, other questions? All right, so I'll just state the corollary. So I just say one thing about the proof is that you can include this category. Question? No. You can include this category into here, right? It's just a subcategory by its definition. It's a fully faithful functor, and it preserves limits. Because limits in sheaves are limits of sheaves, and limits are preserved by extinguishing one. So that formally means that there's a essentially surjective left adjoint to that inclusion, which means that if you generate something here in time 5, then you generate something here in time 5, at most 5. Okay. So this problem actually just reduces to this thing, which can be proven this way. And the lower bound, I won't talk about, but Goodmill probably knows it comes from the ghost level. Okay. Yeah. Okay.
No, I do.
Yeah. Good. All right. So a corollary is Orlov's theorem, and this BES theorem. Okay, so I'm out of time. So I just say corollary is apply this to a torus. You get Orlov's theorem for normal toric varieties. And with a little finesse, you can see, well, the main thing you have to do is show that these probe generators correspond to exactly the sheaves I told you about, right? So we proved that. And then you know. And then with a little finesse, you can see that if I want to resolve an object, I can kind of twist it high enough. And then after doing that, apply this way of generating it from the probe sheaves, and I'll get a resolution by these line bundles on a smooth thing, and in general, some passages. Yeah?
Any other questions?